Hello everyone, this is Mr. Kaviani, and by the end of this video, you should be able to define the relationship between torque, lever arm, and force, and use this relationship to calculate the torque exerted on objects. Before we discuss the concept of torque, I'd like you to consider for a moment how you open a door. This is something that maybe you've never thought of or consciously been asked, but I'd like you to consider all of the different elements that are involved with opening a door. I have a diagram right here that represents a typical door. Let's say we have, in between two walls, we've got a door, and attached to the door is some sort of hinge, right? And this hinge is where the door is allowed to rotate about. So I've got my doorknob over here on the far side of the door, and when you push on the doorknob, it's probably how you open doors, the door begins to swing open. And so what we can say is the door is rotating in this case, right? If you think about the hinge right here as the point or axis of rotation, then when you push on that door handle or when you apply a force to that door handle, the door begins to swing open or rotate. So we could imagine the door doing something like this. Maybe it goes in some sort of, this is not quite to scale here, but some sort of arc like that. And eventually it will be in this open position. And so if we think about the door as an object undergoing rotational motion, then we're able to draw a relationship between the force we applied to the door and how it rotates. So in other words, when we apply a force to this doorknob, when you push on that doorknob or you pull on that doorknob, you're applying a force to the door, and it's allowed to then rotate around the hinge or the place where it's been attached to the wall. So I'd like you to also consider for a moment, why don't we put door handles closer to the hinge? For example, why don't we put one right there? Or maybe you've ever tried to open a door just by pushing on the door itself. Let's say I were to push on the door right here or right here, and I try to push the door open. Is it as easy as it is when I push on the door handle far away from the hinge? If you have never tried this, I'd recommend trying it. Although make sure to keep your fingers out of the door hinge. The reason that we design doors the way we do is because we understand this idea of torque. And in a moment, we're going to define what torque is. But as we do, I'd like you to think about opening a door as an example of a force causing rotation, or what we're about to define as a torque. So as we just discussed, we can use this word torque to simply mean a force that causes a rotation. So in other words, in order for an object to rotate, there has to be some force causing it to rotate. Or in other words, there has to be a torque causing that object to rotate. In the case of opening a door, the reason the door rotates about its hinge is because you apply a force on that doorknob. In other words, you are applying a torque to the door, which allows it to rotate open. We'll get back to what torque is measured in once we have the formula for torque, but it's also important to consider here that just like a force, torque is also a vector quantity, meaning it has a direction and a magnitude associated with it. And so just like we can apply forces in different directions, we can also apply torques in different directions. And we'll take a look at the next slide about how the sign of torque is defined, either negative or positive, depending on the direction that object is rotating in. So we'll see this in a moment, but again, torque can be, yes, positive or negative. And we'll take a deeper look at that on the next slide. So in order to calculate the torque on an object, we're actually going to use this concept of force and also something we're about to call the distance from the hinge or lever arm. So let's take a moment to break down some of those words. I have a diagram on the right of that door, the hinge, and the doorknob. Let's say that I go ahead and I push on the door right here on the doorknob. I'm going to go ahead and call that force just capital F. And because I know that applying that force far away from the door hinge is going to open that door more easily than if I were to push like right here at the door hinge, for example. I've observed that in my own daily life. Then we're also going to factor that into what we call torque. So torque is not just about how much force you apply, but also how far away from the hinge or the center of rotation that you're actually applying that force. And so I'm going to draw a point here from the hinge. I'm going to start here at the point where it's allowed to rotate or where it's actually attached. I'm going to draw a line all the way over here to exactly where I'm applying that force. And so if I look at this distance right here, all the way from the hinge to where I'm applying that force, I'm going to use the symbol R to denote what we're actually going to call a lever arm. And I know this term might be a little bit weird. So R here doesn't mean radius. R actually means something called lever arm, which is a kind of radius. Lever arm, you can imagine almost like the lever or like a door handle. And then arm as if you were to stick out your arm, right? And we have this long distance away from the hinge point. So lever arm just tells you how far from the hinge or the point of rotation you're actually applying that force. And we use, again, the lowercase r to denote what we're going to call lever arm. And so if I wanted to calculate the torque of an object, the torque exerted on an object, all I have to do is multiply the amount of force here that is perpendicular by r, the lever arm. That's all I have to do. Now, we'll get back to this idea of perpendicularness in a second, but I'm going to go ahead and define the symbol for torque. We're going to introduce another Greek letter here. This is going to be what we call tau. So if you say this, say tau. This is not a T with a little tail, although it looks like one. So tau, or in other words, torque, is equal to R multiplied by the force, and I'm going to say the force perpendicular. And again, we'll define these in a moment. So this is going to be my, R is going to be my lever arm. In other words, the distance from the center of rotation. And then again, this F perpendicular is the component of the force that is perpendicular to R, the lever arm, or in this case, the object is the same here. So just to show you what I mean by that, this force is being applied in such a way that it is 90 degrees from the door and also from this lever arm, right? So I'm going to go ahead and draw it's like a big 90 degrees here. And so in this case, this force is completely perpendicular. So there's no component, it just is the whole force. But if I have a force at an angle, which I'm about to show you, I would just take the component that is perpendicular to the door or that forms a right angle at the door. So to show you what I mean, let's pretend that instead of pushing on the door there at the doorknob, you push on the door at an angle, maybe something like this. I'm going to go ahead and just draw this in blue here. You go ahead and just push on the door like that, and that is your force. So I'll call that like an applied force here. Okay. Now, in this case, I only have a lever arm from, I'm going to draw this in blue, from here, right, to here now. So my lever arm is shorter because I'm actually applying that force closer to the door hinge. So my lever arm has changed. But I also can't just use the force applied because not all of that force is perpendicular to the door. It's at an angle to the door and the lever arm, right? The lever arm being that line from the center of the door, the hinge to where I'm applying the force. So I actually have to split this into components right now and find what this perpendicular component would be. But we've been doing that all year, so it shouldn't be a problem. I'm going to go ahead and split this up into a horizontal component like we've done previously. All right, making sure to go from the tail of the vector without the arrowhead all the way to the head of the vector. And I'm going to go ahead and just draw this in another color here. I'll use red to go up. All right, and so if I were to label these, right, I could call this component here my F applied. I'm going to say the parallel. We would call that the X too, which is fine. But in this case, it's parallel. Why? Well, because it's parallel to the lever arm, right, to this line. These are parallel lines. And so that is the parallel component of the force. So by the same logic, this component would be the perpendicular component because it forms a right angle with the door. So this is the component that I need to use when calculating torque. I cannot use the entire force because only part of it is perpendicular, and only the perpendicular part is actually responsible for causing the door to rotate. And so if this angle here, I'm going to do this in black, if this angle were theta, right, then this F applied perpendicular component in this case would be that applied force, right, times, you guessed it, right, sine of theta. This is, again, how we've been solving for components all year. It's no different. If you were to, again, just to preface, right, sine of theta is going to be that opposite over the hypotenuse. So sine of theta here would be F applied perpendicular over the applied force. And if I rearrange for the component here, the perpendicular component, I would get the same thing, right? That F applied times sine theta equals F applied perpendicular. That's where this came from. It came from our definition of sine, which again was opposite over hypotenuse. And so in this case, the torque provided by that force would be this force right here, this component, right here, this one, multiplied by the lever arm here in blue, which is the distance from the hinge to that force. Okay, so our overall equation that you'll need to know, again, is torque, tau, is equal to R, the lever arm, multiplied by the perpendicular component of the force producing that torque. And so once again, I know this is a funky term, but lever arm is the distance from the center of rotation to where the force is applied. One last thing I'll say. You might see sometimes textbooks or other physics resources out there say that torque is just always equal to RF sine theta. And I want to caution you right now. I don't recommend using this equation, and here's why. Typically, as you saw in this example, right, the perpendicular component of the force happened to be F sine theta. But that's only because the angle I was given was the angle between, right, the lever arm and the applied force. So this theta right here. If instead I were given, I don't know, maybe this theta, then you can see that the perpendicular component of the applied force would use cosine, right? Because I was given an angle adjacent to that perpendicular component. So please, I really recommend do not use this equation. Do not just blindly plug in whatever angle you're given into sine. You really need to be thinking about the perpendicular component of force. And we've been solving for components all year, so it really shouldn't be too much of an issue. So I recommend using the equation that you see right here. Tau torque equals R times F perpendicular, the lever arm times the perpendicular component of force. And so because R is usually measured in meters and the force is usually measured in newtons, torque takes the units of measure as a meter times a newton, which, if you recall, was also the unit for a joule, but torque is not a measurement of energy, so we don't usually, we don't say that's a joule, it's just a meter times a newton. All right. Now let's take a second and look at how torque is either positive or negative and see how we define a positive and negative torque.